Good evening, everyone, and welcome to the fifth talk of the Sarabhai Lecture Series, completely online, interactive talk sessions conducted by the Physics Club of SVNIT. Our lecture series is named after Dr. Vikram Sarabhai, the father of Indian space program, a visionary scientist, a great institution builder, and an award-winning physicist, industrialist, and innovator. Today's talk is on phases of quantum chromodynamics and applications to neutron stars. Our speaker is Dr. Andreas Schmitt, an Ernest Rutherford Fellow and an Associate Professor of Theoretical Physics at the University of Southampton. His interests are in quantum chromodynamics at non-zero temperatures and densities, with particular emphasis on applications to neutron star physics. Besides quantum field theory and hydrodynamics, he is also employing the gauge gravity duality to get insight into strongly coupled ultra dense matter. He has published many articles and research papers in several reputed journals. He has also contributed to the book The Physics and Astrophysics of Neutron Stars. On behalf of the entire Physics Club, I'm honored to welcome Dr. Andreas Schmitt. With that, I would like to request the head of SVNIT's Department of Physics, Dr. D.V. Shah ma'am, to please welcome our guest.
A very good evening to all. So, as a higher education institution, the Department of Physics wants to actively contribute directly to the physics community through the series of lectures. So, even though this lecture series is the maker of the success of our department, it also allows us to meet some of the brilliant minds of the country. So I bid a very warm welcome to the renowned speaker, Professor Andreas Schmitt, who took out his valuable time and joined us today to be a part of this lecture series. So the topic chosen, the phase of QCD and application to neutron star, will be productive and worth your precious time. The stakeholders will definitely enjoy. So with these words, I once again thank the Professor Andrews to accept our invitation and enlightening us. Thank you, sir. Thank you very much, sir.
Now I invite Andreas sir to please continue with the talk.
All right. First of all, let me share my screen. Can you see it?
Yes, sir. Yes.
Okay. So first of all, thank you very much for the introduction, the very kind introduction, and the invitation to give this lecture here. So what I want to talk about is a mixture of a more formal topic, namely quantum chromodynamics, and a more astrophysics topic, Neutron stars, and how the two are connected. Already on the first slide, I've put up some example for both sides. So one is the phase diagram in the plane of temperature and chemical potential, which we'll talk about in some detail. And on the other hand, there's a neutron star, or more precisely, the remnant of the supernova explosion. That's most of the colors you see here. The neutron star being a tiny dot in the center somewhere here. I should say that I think you should feel free to interrupt me anytime if there are any questions. I've been told that's mostly for undergraduates, so if I'm too fast or if there's anything that I should explain more, please interrupt me. So what I would like to do is these four subtopics. I'm not exactly sure how far we'll get. This depends on how many questions you ask. If you don't get through everything, that's completely fine with me. It's more important that you follow what I'm saying. So I'm going to start with a bit of a formal part, introducing quantum chromodynamics, a QCD, in very basic terms. So I'm not expecting you to know anything about quantum field theory. I'll just state a few facts and basics of the theory, which we'll then need later. Then I will talk about the QCD phase diagram, which basically means we have to switch on temperature and chemical potential in this theory. And I'll tell you what we know and what we don't know about this phase diagram. There are many things we don't know yet. Part of the phase diagram, since I'm mostly interested in the regime of dense matter, high baryon densities. So in this part of the phase diagram, we expect so-called color superconductivity. So I'll spend a bit of time on explaining what this is. In particular, the so-called color flavor locked phase. And finally, I want to make the connection to compact stars or neutron stars. I was told that you already had or will have a more specialized talk about neutron stars in this series. So I will not really introduce them at length, but rather emphasize on how we can use compact stars as laboratories for the questions that we ask in QCD or in the phase structure of QCD. All right, so let me start with some basics. In quantum field theory, even though, as I said, I'm not expecting you to know quantum field theory, but how a theory is defined is via the Lagrangian, and I'm showing the QCD Lagrangian up here. So together with the rules of quantum field theory, that defines the whole theory. And you see that this Lagrangian looks quite short and innocent, right, for a relatively complicated theory. So let me explain a few of these terms to just understand what the ingredients are of quantum chromodynamics. So first of all, we have quarks in the theory. So the degrees of freedom of the quarks are implemented by the quark spinor, which is the 4 times nc times nf dimensional spinor, where the 4 counts the Dirac degrees of freedom, so spin up, down, particle, antiparticle, right? As you know, for every fermion. Then there are also the colors, which I call nc. In QCD, that's 3. So I could have written 3 from the beginning, but sometimes in theoretical physics, we like to keep this general because there are maybe some theories at large nc which are similar but easier to handle. So often this is kept general, but in QCD, that's 3, the 3 so-called colors of the quarks. And we've got the flavors. Again, I keep this sometimes general and denoted by NF. It's 6 flavors that we know of. I guess most of you know this. Although for most of the applications that I'm going to talk about, only 3 of them are relevant. So for our purposes, also NF will be 3 in most of what I'm going to discuss. All right, so these are the quarks. They do have masses, which are parameters in this Lagrangian. Here I've written down the mass matrix capital M already for 3 flavors only. The mass of the up quark, the down quark, the strange quark. And besides the quarks, we've got the gluons, right? So the gluons are sitting, first of all, here, but also here. So here, first of all, that's the gluonic field strength. If you've never seen this, you will certainly recognize the first terms from usual electromagnetism, right? So that would be a field strength in electromagnetism. Here we are dealing with the so-called non-abelian gauge theory. So there's an extra term, which is the commutator of the gauge field. So these gauge fields are not just scalars, but they are matrices such that their commutator is non-zero. And as I said, the gluons also sit here in the so-called covariant derivative. So there's the coupling constant G, which also appears here. And the gluon field sitting here, which gives us the coupling of the gluons and the quarks, right? Because the gluons are sitting here. They couple to the quarks, and that gives us the interaction between quarks and gluons. Notice that the gluons also self-interact, right? Because of this term. So there's a self-interaction of the gluons as well. As I already said, these A mu's they are not just scalars, but matrices. Here, more precisely, I wrote down how they are written in terms of the so-called generators of the SUNC. So that's the so-called gauge group of the theory that defines the theory. And SU3 has 8 generators, often called TA, where A runs from 1 through 8. And we can write these gauge fields and the gluon field strengths as a linear combination of some scalar functions and these generators. Right, so that's why there are 8 gluons, because this group, this SUNC for NC equals 3, has 8 generators, or is 8-dimensional. That's another way of saying this. Okay, so that's the very basics. That's the Lagrangian. As I said, looks quite innocent, but there's a lot of stuff hidden in there, and it's very complicated to solve this in general. So let's go one step further and look at the symmetries of QCD a little bit closer. I've already mentioned the gauge symmetry. So what we mean by gauge symmetry is a local symmetry, in the sense that the transformations depend on space-time, here denoted by capital X. Right, so by capital X, I mean the 4 vector of time and space. And if I take an element of this gauge group of SUNC, which I can write in this way, e to the something which has the generators here and some scalar functions, theta. If I've got such an element, the statement is I can transform my quark fields and my gluon fields according to these rules, such that the Lagrangian is invariant. Right, and probably most of you have seen this, if not in QCD, then in maybe QED. One way of saying this is that this covariant derivative is just made such that you get an invariant, this invariance under the gauge group, because the derivatives will now see this X dependence up here. Okay, so we've got our gauge symmetry. That's maybe the most important symmetry of QCD.
Excuse me, sir.
Yes.
So, do we get any conservation laws from the symmetry, like from Noether's theorem and all?
Yes, but this is for the global symmetries. I'm coming to these right now. Right, so this is for the global symmetries, also for the local ones. So things like charge conservation, as you know from QED. But let me explain this for the local ones. So here's the other symmetries, or I've summarized all symmetries of QCD here in this line. So the blue one is the gauge symmetry that we've already discussed up here. And then I've added something in red here, which is called the chiral symmetry. So let me explain this for a second. So what you can do is you can define so-called left and right-handed spinors from the original spinor psi by multiplying with these projectors, projecting onto right and left-handed chirality. That's the definition of them. And if you do this, if you decompose each of these psis as psi right plus psi left, then you find that the Lagrangian is also invariant under this global symmetry, however, only for 0 mass. Right, so here's a little a subtlety. This symmetry is not true if you have a mass of the quarks, which we do have. So you might ask, why am I telling you about this? Because the mass is non-zero in QCD. So this term, if you do this little exercise indicated here, you will find that the term with the m does not become invariant. But if m is 0, then the Lagrangian is invariant under this global symmetry. And so what I mean by SUNFR is the transformations, the SUNF transformations acting on psi r, and the same for this SUNF left, right? So why is that still interesting? Well, it's interesting because there is a sense in which this symmetry is approximately, is an approximate symmetry, because the masses, at least for up and down quarks, are small. right? So that it's still a very important concept, and I'll get to that in a sec on the next slide. I think it's still a very important concept for QCD, for the understanding of the properties of QCD, to introduce this chiral symmetry, even though it's not an exact symmetry due to the masses. Moreover, here's another group here. So if you do this little exercise with the chirality, what you actually get is an invariance under UNF cross UNF, which you can write as SUNF cross SUNF cross U1 cross U1. One of these U1s is the so-called baryon number conservation, which is exactly coming back to the question you just asked. One of these examples where you have a symmetry, a global symmetry, and this is associated with a Noether current, in this case, baryon number conservation, which is always exact, right? This is not destroyed by the non-zero mass. There's another U1. I will not come back to this later, but let me mention this for completeness. The U1, so-called axial U1, under which the Lagrangian is also invariant, but this is broken on a quantum level. You may or may not have heard about so-called chiral anomalies. Just for completeness, let me mention this. So this U1A does not appear here because it's broken on the quantum level. So these are the symmetries that are relevant for QCD. The red part, as I said, only approximate. And also remember the distinction between a gauge symmetry, which is local, and the global ones, which are the red and the black ones. Okay, so here's an example why it's still useful to think of chiral symmetry, even though it's not exact. So here's something you might have seen already in your lectures, spontaneous symmetry breaking. Let me explain this in very brief words in this little sketch. So with this little sketch, I'm indicating a theory which is invariant under some group, let's say G. Think of this as rotating around some horizontal axis, some vertical axis, right? So this dashed line indicates that it's supposed to be three-dimensional, so there's a symmetry with respect to rotation around some vertical axis. And notice that both potentials, so let's say these are some effective potentials, and the horizontal axis or the plane is some so-called order parameter. So both of these potentials are symmetric under this rotation, but the red one has a ground state sitting here, whereas the blue one has a ground state sitting here. And the difference is the blue one, this ground state here, is not invariant under rotations around this circle, right? I've broken the symmetry. Doesn't really matter where I put this the blue point, right? Because it's all the same energetically, but it will break the symmetry. It has to sit somewhere. Right, so this means there may be a regime of the theory, let's say at large temperatures, where we are in the symmetric phase, and there may be a regime of the theory, usually at small temperatures, where we break this symmetry spontaneously. Spontaneously is the term for that, meaning the Lagrangian is invariant under this symmetry, but not the ground state for a certain regime like small temperatures.
Is it important to have two grounds?
Yes.
Is it important to have two ground states? Like for the blue one, we can see two points coinciding with that rotation.
Yes, what I wanted to indicate with this sketch is that there are infinitely many even, right? So it's not supposed to be only two, but every point on this circle is a ground state, would be a valid ground state. Does that make sense? So think of this as a three-dimensional plot. So there's like a bottom of a wine bottle shape. And as I said, yes, this is important because otherwise the symmetry would not be symmetric. But which point the system picks doesn't matter. They are all degenerate. Does that make sense?
Yes.
Okay, so
that is a
yes?
It's a biquadratic term in the Mexican hat, right? The parabola, the quadratic, and the other one was the biquadratic.
Exactly, that's what most of you probably have seen already. So this is often done in a simple model in the 5⁴ theory, where here there's just positive signs of the quadratic and the quartic terms, whereas here you have a negative quadratic term and a positive quartic term. Yes, exactly. Yes. I didn't even want to get that technical. I just wanted to show you with a picture, but yes, that's absolutely right. Yeah. So what you can also use this for is that for a prediction of so-called Goldstone modes, which are massless modes in the spontaneously broken state, I wrote this in a relatively abstract way, namely as the dimension of this so-called coset space, which is the original symmetry group, U1 in this case, right? This circle is just a U1. I'm simplifying here. And the broken group H is just a trivial group. So there's no further symmetry associated with the ground state. So that's why in this particular example, you would have only one Goldstone mode. If this was a bit confusing, let's look at QCD. I think it becomes clearer in this richer theory. In this case, we have something similar, but in a much more complicated space or with more complicated groups. In this case, it's the order parameter is the so-called chiral condensate, an expectation value of a quark-antiquark pair composed of a left and a right-handed quark and antiquark. And this spontaneously breaks the chiral symmetry. Let's suppose it's exact for a second, but it spontaneously breaks the approximate symmetry. In this picture, that would mean the whole thing is a little bit tilted, right? It's not an exact symmetry, but it would be a little bit tilted. But it breaks it not completely, it breaks it down to a residual group, right? So this is now hard to draw, right? So there are many more dimensions involved, but what this means is this circle, these rotations along the circle correspond to this, and then some residual rotations, which are still possible and leave this ground state invariant, is this side, right? And again, we can just count dimensions of this group. This is 8 plus 8, and dimension of this group, this is also 8. So we have 16 minus 8, which are 8 Goldstone modes from this spontaneous chiral symmetry breaking for NF equals 3. I should have said this before. So I've written down this in general for general NF. But if we talk about NF equals 3 flavors, then it's 8 plus 8 and 8 here. And that's nothing but the mesons that you all know, I assume, pions, kaons, and the eta. They are not called Goldstone modes because they're not exactly massless, as you know, they do have a mass. In this case, one calls them pseudo-Goldstone modes, referring to the fact that the symmetry we've started with was not an exact one. But it's still useful as a concept, for example, to explain why these masses are relatively small. So this is what chiral symmetry breaking does. A similar thing applies to confinement. I will remain a bit more vague here. There's also something like an order parameter, in this case, the Polyakov loop, and it breaks a discrete symmetry called the center symmetry. Also, this one is not exact. It's only exact if you neglect the quark. So again, it's some concept that doesn't strictly apply to real-world QCD, but which is very useful to have in mind. So both chiral symmetry breaking and confinement can be understood in this context. Okay, before we get to the phase diagram, one more important property. This looks a bit formal, but I will go through this very briefly. So this is asymptotic freedom, very crucial property of QCD discovered by these guys here. I'm sure you've heard these names. They got a Nobel Prize in 2004, I think, for this discovery. So if you play the rules of quantum field theory, I will not go into any details. You do the so-called renormalization. What you find is that your coupling effectively runs with the energy scale, right? Remember this coupling constant in the QCD Lagrangian, but effectively, if you really do physics with it, it is a coupling that depends on an energy scale Q or momentum scale Q. And this is given by the so-called beta function. Never mind the details. There's an expansion in alpha S, which is the coupling constant squared over 4 pi. And you can truncate this series to solve this differential equation. So this can be done, and you have to fix a renormalization point because alpha S of Q is only determined relative to some points that you have to fix from experiment. So never mind the details. The most important thing is this plot here. So this is the effective coupling of QCD as a function of an energy scale. And you see it goes down as we go to high energy. Remember from the uncertainty principle, this will, or high momentum, this corresponds to low distance, small distances. So if I have two quarks and bring them closer and closer together, they will interact more and more weakly. This is what asymptotic freedom means, right? Asymptotically, quarks are free if they are only close enough to each other, right? So asymptotic freedom refers to the fact that this gets arbitrarily low here, and quarks and gluons become free at small distances or at high momenta. So this also means, that's interesting for the theory, that also means that we can use perturbative methods. So we know we can do very controlled and relatively easy calculations here, but as the coupling gets stronger, the calculations become more and more difficult. That's why I said at the beginning, even though the QCD Lagrangian looks quite innocent, there's a lot of complications and many regimes where we can't do first principle calculations. For example, confinement is a consequence of this, right? So now let's look at this from the other way around. Let's start at low distances and try to separate the quarks. The more I try to separate them, the stronger the interaction becomes, right? In other words, I would need infinite energy to separate them in the confined regime, and that's the confinement in simple words. It's exactly the same confinement that I introduced here more abstractly. So think of it in this more physical picture if you want. All right, so this was the basics of QCD itself. Are there any questions at this point?
No.
Okay, then let me now go to phases of QCD. So what we are now basically doing, so when we do, let's say, usual particle physics with QCD, we are interested in single particles, right? Properties of single particles, collisions, cross sections, and so on. But what I want to do now is I want to use QCD to describe matter, right? Or in other words, a system of infinitely many quarks and gluons, just like a condensed matter system, as you know from solid state physics, for example, right? So now I'm looking for systems that are infinitely large in the sense that we neglect any surface effects for simplicity for now, have infinitely many particles and which are governed by QCD, right? So first of all, completely theoretically speaking, how do we do this? Well, we apply a formalism called thermal field theory. I've put 2 lecture notes here. I have some unpublished notes. If you're interested, feel free to write me. I'm happy to share them. But there are also some books about this. That's one recent one about thermal field theory, which basically means how to generalize ordinary quantum field theory to non-zero temperatures and also chemical potentials. Here I put mu B for baryon chemical potential. So in a way, what we are doing is we marry the quantum field theory with statistical physics, right? So remember from statistical physics, the central quantity was the partition function Z, defined as a trace over this operator. Beta is the inverse temperature. That's the Hamiltonian, and the particle number operator, chemical potential. So that's what you do. And once you have this partition function, you basically have all your thermodynamics. You take derivatives of this partition function, or of the log of the partition function, and you get thermodynamic quantities like energy density, entropy, and so on. In quantum field theory, what we do instead is we write the partition function as this functional integral over the fermionic quark fields and the gluon fields, and have our action e to the action. So the space-time integral over the Lagrangian is the action. And one thing I want to point out is that the way the chemical potential enters is like this. So here I've written down the Lagrangian again. but now with the chemical potential added. So you see it enters a bit like a temporal component of a gauge field sitting in here, right? So there's these gamma matrices here, gamma mu. You see this comes with a gamma naught. This all, I mean, I'm not really explaining this. One would have to go through the calculation, but from this here, one can derive that the chemical potential enters in this way. So when I say chemical potential in QCD, of course, with 3 flavors, we have separate chemical potentials for up-down strange, because they are separately conserved unless we also add the weak interaction, which can change the flavor. So in principle, there are 3 of them. When I say mu baryon, then I mean the average of them. You can, roughly speaking, think of them to be equal. It doesn't matter for the next few slides. So what I've also introduced is so-called imaginary time. So this space-time integral is not a usual space-time integral. I've Wick rotated, in a sense, to imaginary time, which goes from 0 to 1 over the temperature. Obviously, don't confuse this beta with this beta function here, just to be clear. So this is just 1 over the temperature. And this has interesting consequences because we have periodic or antiperiodic boundary conditions for the quarks and the gluons on this imaginary time direction. So it's as if we have compactified the time direction. And the reason is that is this trace here, which has which you can think of as sum over expectation values of the same initial and final state. If you think of this as a unitary time evolution matrix here. So we need periodic boundary conditions. And this means if you're on a compact space in the time direction, you will get discrete energies, right? Think of a particle in the box, which has discrete energy states. So you have discrete energies or 0th component of the 4 momentum, and they are called Matsubara frequencies. So when you do momentum sums, you will have to do a discrete sum and then an integral in the thermodynamic limit. So this is admittedly all very quick. So this was just to give you a very rough idea how this works, and mainly to show you that it works, that we have a well-defined way. Once we have a given Lagrangian, there's a well-defined way to introduce temperature and chemical potential. All these details we will not need later. And if you've never seen this before, I admit this is all a bit quick. But we do have a well-defined way to introduce temperature and chemical potential. Okay, so now you might say, okay, let's calculate something, and indeed there are, even though that's very difficult, there are, if you wish, brute force evaluations of this partition function by putting it on a space-time lattice. Importantly, this is done at mu b equals 0, because as I wrote down here, at non-zero baryon chemical potential, the usual methods for the so-called lattice gauge theory, some probabilistic methods they use to evaluate the integral, they do fail. That's the so-called sign problem. But if you set mu b to 0, what you can do is you calculate the partition function, and you get thermodynamic quantities like the pressure as a function of temperature. That's the blue line here, or the entropy or the energy density shown here. These plots have several details which are not so important to us. One interesting detail, though, is these arrows here indicate the limit of free quarks and gluons. So remember asymptotic freedom. Asymptotic freedom meant if the particles are close enough to each other, they get weakly coupled, right? Free in the asymptotic limit. This translates into the large temperature regime, right? Large temperature means there's high energies, particles get close to each other. So at asymptotically large temperatures, we expect the theory to be asymptotically free. So this blue line will approach to this value indicated by this arrow up here. And the same here. The yellow curve will approach to this. You see it's quite slow, but still it will approach. Okay, so for us, it's important to keep in mind that these lattice methods do not work at non-zero mu b, and that's one of the reasons why there are so many open questions about QCD at finite baryon densities. Okay, so let me now get to the phase diagram. And I've brought up a very simple version of the phase diagram. Basically, what this means, so this is the phase diagram in the temperature and chemical potential plane. So what this means is if we have very large mu and or t, we know we are asymptotically free, right? So there can't be any confinement, and chiral symmetry is also restored. So this is a phase of quarks and gluons. Whereas if the coupling gets stronger and stronger, we know there has to be some kind of transition here, schematically shown by this line. I've not even put any numbers yet here. And below this line, we are in the confined phase or hadronic phase, where quarks are confined in baryons and mesons, right? So that's what we know just from very simple property or fundamental properties of QCD. Some kind of transition must happen here. But where does it happen? What kind of transition is it? And what do we know about that? So
Hello,
here's
sir.
a bit more. Yep.
So you mentioned that the chiral symmetry breaking takes place due to non-zero quark mass, right? So how come deconfinement will restore that chiral symmetry?
Well, one simple way of saying this is that both of them are strong coupling phenomena, right? So strong coupling kicks in at some scale, say here, and strong coupling leads to confinement and chiral symmetry breaking. I'm not saying they are necessarily coupled, even though it looks like this here. There may even be two different lines, right? So I'm not really saying deconfinement leads to chiral symmetry restoration. I'm just saying if the CO is weakly coupled, we have deconfinement and chiral symmetry restoration.
So you're saying that there might be phases where it is deconfined, but still the chiral symmetry is broken.
Yes, yes. I mean, in these intermediate regimes here. I mean, I'll get a bit more. Let me get to this question right away when I show you some more details. So these are a few more details now. As I told you, if mu is 0, we can do lattice calculations. And what we know is that this transition that I indicated here, or both of these transitions, are actual smooth crossovers. There's no real phase transition line here. And we roughly know the location of this crossover, which is about 150 MeV. So coming back to your question, if it's a crossover, if the order parameters do not jump or don't go to from exactly 0 to some value, they just behave a little bit like these curves here, right? And you can't even really define where do I have confinement or deconfinement. It's smooth. There is a region where the order parameters change significantly, but still they are smooth. So in this sense, there's no real strict phase transition temperatures, critical temperatures for these two transitions at mu equals 0, right? So that's one thing to learn from this more detailed phase diagram. The other thing is I've indicated in black all the things we know, and you see there are not very many. All these blue lines, the pale blue lines here, are conjectures. What we do know is, and that's also interesting for Neutron stars later, is that there is some phase transition here from, let's say we are at 0 temperature, where this is the vacuum. At some point, mu gets large enough that we can put baryons into our systems, right? Nucleons, neutrons and protons. So this is nuclear matter here. And there's something like a liquid gas phase transition that separates these two phases. The fact that it ends in a critical point tells us it's not related to any symmetries. It's just a density jump going from one side to the other. And it happens about this value. How to understand this value? Well, this is, here I put quark chemical potential multiplied by 3 to get the baryon chemical potential. So if the baryons were non-interacting, it would be the baryon mass, right? 939. but there's a binding energy, 16 MeV, so 939 minus 16, and then divide by 3 to get the quark chemical potential. That's how this number comes about. What we also know, because as I told you, if mu is very large, or T, then we can use weakly coupled methods, weakly coupling methods. And we know that at very large mu, there's a phase called color flavor locked phase, and I'll talk about this in a few minutes. That's one of these color superconducting phases. Other color superconducting phases may appear here schematically summarized as non-color flavor locked. Nucleons are also supposed to form Cooper pairs, so you can have nuclear superfluidity. And this line here corresponds to this line here. So we don't quite know where this sits. We don't even know whether it's first order. If it's first order, it has to end at a critical point because we know it's a crossover here, right? That's what I told you. So there must be some kind of transition here, but we don't really know where it is. Again, remember, lattice QCD doesn't work here. In fact, on the next slide, I'm showing the theoretical methods we have. So I've already told you that lattice QCD works for 0 mu. There are some improvements recently to try to extend this to finite mu. That's what I try to indicate with these arrows here. But if we're interested in the dense regime, which is the relevant one for neutron stars, which I will come to later, then lattice QCD is currently of no help. We do have so-called chiral effective theory, where we use input from experimental nuclear physics. So at low densities, we can describe nuclear matter. And at extremely high densities, we have perturbative QCD, as discussed, because of asymptotic freedom. So these arrows indicate we can extrapolate down or up these results, but we don't have any controlled first principle calculation in this intermediate regime. So that's the interesting regime, which is neither described by, let's say, ordinary nuclear matter physics, nor by weakly coupled perturbative QCD. And that's also interesting because where are the experiments we can do? Well, on Earth, we can only really do heavy ion collisions, which is smashing together heavy ions. What this creates is the so-called quark-gluon plasma at relatively high temperatures and low baryon chemical potentials. Whereas in this region here, for very large baryon chemical potentials, the only laboratory we have are really neutron stars, which are on this scale here, on the QCD scale, which are cold, sitting down here. However, very recently, through neutron star mergers, we can also probe a regime which is dense and hot. This is related to gravitational wave detection, which I'm sure you've all heard about in the recent years. So now this gives us a new window into the QCD phase diagram in this intermediate regime here. Okay, any questions about the phase diagram?
So in layman terms, could you explain why lattice QCD fails for high mu's? What exactly happens that causes it to fail?
I'm also not an expert in lattice QCD, so I would also have to check the details. But what they do is they use some Monte Carlo methods, so some statistical methods to evaluate a highly multidimensional integral. And if the chemical potential is non-zero, then these methods fail. I guess that's the short version of it. Why it fails, we would have to write down some formulas. I would also have to go back to that and check it myself. But that's the reason we can't use these sampling methods that they use to evaluate the highly multidimensional integral, which is needed to be evaluated for the partition function. And then there are ways, recently people have tried to circumvent this sign problem or find slightly different theories where it's a bit milder. So there has been progress, but currently, indeed, we cannot really use lattice for high densities. Any other questions? Okay, I want to say a few words about color superconductivity. I guess I'm going to be a bit faster here and get to the neutron stars at the end. So what is color superconductivity? First of all, remember from your condensed matter lectures, what is Cooper pairing of fermions? You've got a Fermi C, which is filled up to the chemical potential at zero temperature, the Fermi energy, and look at the free energy of this system, which is E minus mu n. If I add a fermion at the Fermi surface, I can do this without energy cost, right? Because this is negative. If I add one fermion where n is 1, I subtract mu, but I also add mu because of this term. And this means there's an instability at this point. So if there's an attractive interaction between the fermions, I can add a pair with an energy gain. And that's, in simple words, what happens if I have Cooper pair condensation, right? You know this from electronic superconductors where electrons form Cooper pairs in a metal. But this mechanism is very general. Here I've not used the fact that these are electrons or quarks or anything. So I can apply the same argument for quarks as long as I have this sharp Fermi surface, right? The temperature has to be sufficiently small. And I need an attractive interaction, which we have in QCD between the quarks in a certain channel. So that's why we believe quarks have to form Cooper pair at sufficiently small temperatures and high densities. And of course, now you have to ask yourself, quarks are of course more complicated than electrons. For electrons, maybe you remember you just have a Cooper pair of spin up, spin down electrons. But now quarks have not only spin up, down, they also have color and flavor. Right, so the question now is which quark forms a Cooper pair with which other quark, right? Because there are many quark species, 9 if we have 3 colors, 3 flavors. So this question can be answered by these rather formal arguments here. Let me briefly go through this. If you, by the way, if you want, this is a review that I wrote a while ago about color superconductivity. So what we have to check is the coupling of 2 quarks. Maybe this notation you're familiar with from particle physics when you discuss mesons, where you couple a triplet with an anti-triplet. That's quark anti-quark pairing. But here we have 2 triplets because we have diquarks, right? It's not quarks and anti-quark. It's really 2 quarks at the Fermi surface at high densities. And this can be decomposed into this antisymmetric anti-triplet and a sextet. This one is attractive, so this is the one we pick. And in the flavor channel, we have the same group or representations of the SU3 for 3 flavors. And we also pick this antisymmetric anti-triplet because of symmetry reasons, because we want to have spin 0 pairing, right? So our Cooper pair should have spin up, down. So total spin 0, which is an antisymmetric channel. And together with these 2 antisymmetric channels, this gives an overall antisymmetric wave function. What this means is that we can write the order parameter, the diquark expectation value, in an antisymmetric sector from this part, the color part, and an antisymmetric sector from the flavor part, and some matrix that couples them and determines the pairing pattern of the quarks, right? So now whatever I choose for this phi tells me which quark species forms Cooper pairs with which other quark species. And it turns out the only possibility to make all quarks participate is to insert a Kronecker delta for this phi. And that's called the color flavor locked or CFL order parameter. You can already understand it from here because color and flavor indices are locked, right? Blue is flavor, red is color. And here's the pairing pattern. So you form Cooper pairs of green strange quarks and blue down quarks and so on. And you have this interesting structure of these 3 quarks here. It's also still Cooper pairs, but still it means the quasi-particles are linear combinations of all 3 of them, even though I'm only forming pairs, right? But such a structure is necessary because we have 9 quarks, right? And in this way, they all participate in Cooper pairing. That's why this is the most favorite phase at large densities. And we can discuss a few properties of this. Here also the symmetries become very useful. So this side is the symmetries of QCD that we've seen before. I've added electromagnetism, which is also a gauge symmetry. Now the gauge symmetries are red and the global symmetries are blue. And we can read off a few things here. First of all, chiral symmetry is broken also in the CFL phase, but for a different reason, right? Here we do not have a quark-antiquark condensate, but a quark-quark condensate. Nevertheless, through the locking to color, we get this residual group from the chiral symmetry here. So we also have Goldstone modes in that phase, right? Kaons, pions, and so on. Not identical to the original ones, but having the same quantum numbers. CFL is a superfluid, which we can read off of the breaking of the U1. If you learned, if you had a lecture about superfluidity, you remember maybe that this can be characterized by spontaneous breaking of the particle number conservation symmetry. This has all kinds of consequences. There's an exactly massless Goldstone mode because this is an exact symmetry. There are vortices like in an ordinary superfluid if you rotate CFL, which is relevant for neutron stars. There's also an interesting thing happening to electromagnetism. I don't really have time to go into the details. But what this means is the gauge groups, the red ones, are broken down to this one here. This means there's a Meissner mass for 8 of these gauge bosons, right? It's the gluons, the 8 gluons plus the photon. 8 of them have a Meissner effect. That's why it's called a color superconductor. But one of them, which is a mixture of a gluon and the photon, remains massless. This may sound quite fancy, and maybe it is, but you may have seen this in the standard model in the Higgs mechanism. It's very analogous, where you break SU2 cross U1 to the electromagnetic U1. Something similar happens here. Excuse me, I've been ill for a few days, so my voice is having a hard time. Okay, so these are the basic properties of CFL. I wanted to say a few words about stressed Cooper pairing. Let me skip this to have more time about the neutron stars. So this is basically explaining what I call non-CFL here. Let me just say, if you go down in density, starting from the color flavor locked phase, you will find that CFL no longer becomes preferred, but you rather have different kinds of pairing patterns. And if you use certain models, you get a very rich phase structure here. But this is model dependent. That's just this is the so-called number Jonas-Lasinio model, which is not a first principles calculation. So this is just to get an idea of how the phase structure might look like. And maybe it's not so surprising that this is very complicated, right? If you think of phase diagrams of other substances like water, all these different kinds of ice, that's a horribly complicated phase diagram. And QCD might be similar at high densities. It's a bit like condensed matter physics of QCD. So it shouldn't be too surprising that it looks can look quite complicated. But let me use the last 10 minutes to bring neutron stars into the game. So here I've quoted lecture notes that I wrote a while ago. If you want to have a look, so this is about dense matter and compact stars with the emphasis on the dense matter, but there are many applications to the physics of compact stars. So when I say compact stars rather than neutron stars, then I'm allowing for more exotic possibilities. So when astrophysicists usually talk about neutron stars, what they mean is a star which is entirely made out of, let's say, ordinary nuclear matter, right? The point being, of course, when I say compact star, then I mean a star of with radius of the order of 10 kilometers, with a mass of between 1 and 2 solar masses. So it's an incredibly compact object, right? But that's exactly what we need to probe these regions of the phase diagram we were discussing before. So this is, the matter is so dense that the nuclei overlap, right, of the atoms, and maybe even the nucleons overlap such that quarks and gluons become the relevant degrees of freedom. That's the connection to the QCD phase diagram. What we might also have, and that's why I'm saying compact stars to be more general, is we may have a quark matter core inside the neutron star, right? So let me go back to this picture here. So when I put the neutron stars here, we roughly know where the red blob sits here, even though this picture is, of course, very schematic. But we roughly know the densities, but we don't really know where this transition is between confined and deconfined matter, right? So we just don't know whether neutron stars have this form or this form, whether there's a deconfined quark matter core. So this is usually referred to as a hybrid star. And the most exotic possibility, also we can't exclude this yet, is that there are quark stars in the universe, sometimes called strange stars, because this is made of up, down, and strange matter. Okay, so why is that interesting for us when we do QCD or QCD phase diagram? Well, we want to relate an observable quantity, that's the blue ones here, to a microscopic quantity that we compute either from QCD or from some models, some effective theories. I will not go through all of these. I will show you an example of mass and radius. There are others just like the temperature, which is related to the neutrino emission of the matter. Gravitational waves are, of course, very prominent recently. They can also be related to microscopic properties. In general, one distinguishes between so-called transport properties, for example, viscosity, which are sensitive to the low energy excitations, right? So that it matters what the excitations are at the Fermi surface, right? And this can, for example, distinguish between Cooper pairing and non-Cooper pairing. And the other class is the thermodynamic or bulk properties, where the whole Fermi sphere matters, like the so-called equation of state, which is the pressure basically as a function of energy density. So these are the two classes. In general, transport properties are even harder to calculate. Thermodynamic properties are easier, at least in a certain model. Within QCD, also this is, of course, difficult. So let me give you this example of the mass radius curve. So what we can do is we compute the so-called equation of state, P of epsilon, in principle, ideally from QCD, although we can't do this. So epsilon is the energy density, P is the pressure. And we couple this to gravity, that's the so-called Tolman-Oppenheimer-Volkoff equations, and we get a relationship between the mass and the radius of the resulting stars. And importantly, each of these curves predicts a maximal mass. So let's look at these plots here. So this is the mass of the star, this is the radius. And each line is the mass-radius relation for a given equation of state. Right, to use different models. As explained, we can't use first principle QCD, so you use a specific model, compute an equation of state, and you see all of them have a maximum mass. Why is that interesting? Well, because we have some mass measurements of very heavy stars indicated by these lines here. You see the radius is not known at all for these stars, so that's why they are horizontal lines. But it already means that all these curves that can't reach this point can be excluded, right? So in this plot, I can already exclude all these equations of state that have maximum mass below these ones that we know from data. We can use this, for example, this has been done in this paper here. We can use this to constrain the equation of state. So what these people have done is they've used chiral effective theory for nuclear matter at low densities or low energy densities. This one is pressure here. And perturbative QCD due to asymptotic freedom here. And then they've just said, let's forget about any microscopic model. Let's just try to interpolate in all possible ways. They just used piecewise polynomials, but many of them, thousands of them, and try to constrain this by the astrophysical constraints we have on mass, radius, also the so-called deformability from the neutron star merger, and some consistency conditions such that, for example, causality, speed of sound has to be smaller than speed of light, and so on. And you see, even though we know very little about the microscopic physics in here, we can constrain this relatively well already by these constraints. So that's just to illustrate one of the ideas that are being explored in current research. Finally, let me say a word about neutron star mergers. I've already mentioned this. So what people can do is they can do real-time simulations in general relativity. Here I've used some plots from a group of our university in Southampton, where they made some plots of temperature or electron fraction or density for two different times of the merger process, right? So we have two neutron stars which orbit each other, but they at some point merge and in the process radiate gravitational waves, and they have been detected recently by LIGO, right? That's the simple picture. And of course, now we would like to see whether from the gravitational wave pattern we can conclude something about the matter inside the neutron stars during that merger process. For example, when they do such a simulation, they can map out temperature and chemical potential of the matter during the process. And as I said when we discussed the phase diagram, by the mergers we probe also higher temperatures. So this is you can see here, we go to much higher temperatures than we usually go in isolated neutron stars. And you can use this to ask questions, and that's what people are doing in current research. Is there an effect of a quark-hadron transition? Can we observe a quark-hadron transition through the gravitational waves? Do we have to include dissipative effects in these kinds of simulations, like viscosity? And then there was a merger where one of the objects was determined to have 2.5 solar masses, which is very unlikely to be a black hole, but which would be very heavy for a neutron star. Suppose we had a line here at 2.5, you'd see that most equations of state would have a very hard time explaining this. So this is one of the current questions. Okay, so this is just to illustrate what people are doing in the field of QCD applications to neutron stars. So as a summary, I just tried to pick a few general statements that as take-home messages. So I told you a bit about QCD itself. It's a fundamental theory of the strong interaction, right? As you know, there are four fundamental forces. QCD describes one of them. It's a theory of quarks and gluons, and we have a well-defined way to include temperature and chemical potential. We can ask the question, how does the QCD phase diagram look like? What are the phases? Many open questions remain. Examples for such interesting complex systems which are governed by QCD are compact stars and heavy ion collisions. And I've tried to illustrate a bit how astrophysical data from compact stars can be used to understand more about QCD matter. Okay, so thank you very much for your attention, and obviously I'm happy to take more questions now.
So I was wondering, sir, there is any experimental possibility of detecting, finding out if the given matter is in quark-gluon phase or not? Any kind of
Yes.
experiment that allows us to determine this?
That's a very good question, of course. I mean, the short answer is we don't know yet. But one idea is this one, that you try to do this simulation with and without such a quark hadron phase transition and see if there's any significant difference in the gravitational wave signal, right? That's difficult, but people are trying to do this. What you also have to ask, of course, is where do these phases give very different results, right? Equation of state, maybe viscosity or superfluidity. Here also it's not so easy, but of course you do find different properties, whether you have nuclear matter or quark matter for things like viscosity. Of course, the big problem being is that suppose you want to describe deconfined quark matter, you have to use a model, right? So there's always a large uncertainty because we can't do QCD in this density regime. So this is, of course, one very good question, but the answer is very difficult. But I would say there's certainly progress recently, in particular because of these better astrophysical data, either from gravitational waves, but also from radius measurements. I completely ignored this here, but we do have some radius measurements from very recent data, which also help to narrow down mass and radius of the star.
So if I'm not wrong, what you're trying to imply is that since we don't have a proper model for the quark-gluon plasma or the phase transitions, there is no way we can predict any experiment that can differentiate it from normal quark matter, right? We can't be sure about that.
That's the pessimistic point of view, yes, but it's not wrong. Yes, of course we can apply some effective theories, extrapolate them, right, to get some idea, and then look at the predictions of these models, and that's what people are doing.
So what about the progress in creation of quark-gluon plasma in LHC? Like there has been news recently, like they have calculated the viscosity of QGP in LHC. Like I'm sure they're probing the low density phase, but not the high density phase. But is there any way to extrapolate those results to the high density phases also?
Yeah, good question as well. So as I showed here in the phase diagram, as you said, the heavy ion collisions live at these higher temperatures. But notice I've already indicated with an arrow here that people are trying to extend this. So there are facilities being built, one in Germany in Darmstadt and one in Dubna in Russia, trying to create the quark-gluon plasma at higher densities. And you're right that they try to extract things like viscosity. So it turned out the viscosity is extremely or surprisingly low, at least in the, relatively speaking, in the correct units. Extrapolating this to very high densities is a bit of a stretch because the physics at high temperatures it can be very different from high densities, but it can be used to restrict our models and give some input into the models that we're using. So in this sense, we should not forget about the results here if we talk about this region, but a direct extrapolation is difficult, I think.
So I don't know if I'm wrong, but what I was thinking is that in speaking relativistically, high temperature or high energy is equivalent to talking about high densities, since there will be particle antiparticle creations, and so a high energy indirectly implies high particle density, since there will be particle creation. I mean, particle antiparticle pair creations. So what exactly is making high density different from high temperature in this case? I'm not able to get this.
Okay, that's a good point. I haven't made this completely clear. What you say is completely right. If I say, well, high temperatures, exactly, it means that there's a lot of quarks and antiquarks, particles and antiparticles. But when I said density in this talk, what I meant is high baryon density, which means that there's an imbalance between matter and antimatter, so much more matter than antimatter.
Okay, so this mu, whatever it's here, it's talking about the mismatch between the number of particles and antiparticles. I mean, quarks and antiquarks.
Exactly. That's what the chemical
It's not the
potential.
total number. It's not the total number, right?
Sorry, I didn't understand the last part.
It's not the total density of particle and antiparticle, but it's a mismatch between them, right?
Well, when you say total density, that would be zero, right? Because they would cancel each other if you ask for the baryon density. But if you talk about energy density, that's also very high at high temperature, as you say. But yes, the chemical potential, that's what it does. It creates a bias towards particles compared to antiparticles, yes. So a neutron star is basically at zero temperature. It's basically only made of baryons and maybe quarks, but antibaryons or antiquarks play no role. Whereas in the quark-gluon plasma of the heavy ion collision, there's almost the same number of quarks and antiquarks.
Professor Andreas, I have a doubt on. Can you go back to the slide where you explained about the thermal partition function?
Yes.
Yeah. Okay. So what I was basically thinking was we have the thermal partition function and we add few symmetries. And is it possible to get the correlation function and do some sort of a calculation with that with respect to the dimensions, the scaling dimensions?
I'm not sure I completely understand what you want, but basically you can do everything that you do in ordinary field theory, you can do now in thermal field theory with this partition function. Yes.
Yeah. So so you actually did the weak rotation down below. So what I was basically asking is can we add up few symmetries and with okay, let's have a system having a certain thermal partition function and add few symmetries to the weak rotation and employ to study the particular system, how it behaves with that symmetry.
I still don't quite understand what you mean by symmetry. I mean, if you calculate the partition function, the symmetry, you don't have to care about the symmetry.
Okay. No, for example, when we do the conformal field theories, we add symmetries to the partition function and we try to get the correlators and you try to
Yes.
study the system based on that. So is the same method possible in case of QCD calculation?
You mean adding source terms and things like this?
Yes, yeah, exactly. Yeah.
Yeah, of course. I mean, the rules of field theory are still applicable, right? So all I've done, I've compactified the time direction. But now you can do your usual field theory. You can calculate loops. You have Feynman rules, which are very similar but slightly different to the zero temperature field theory. Yes.
Yeah, and the main reason for me to ask that question was because you discussed about the chiral symmetry, and when we have the Weil symmetry there, it goes for the chiral anomaly. So, how does the system behave in that aspect?
Well, you do see chiral symmetry breaking, right? You can calculate the expectation value of psi bar psi, for example.
Okay.
So that's the formalism with which you calculate things like this psi bar psi here.
Okay.
Right. I mean, that's very difficult, but at zero chemical potential, this can be done on the lattice. But that's the formalism you use. Yes.
Yeah.
I have a question. You had already mentioned that chiral symmetry breaking takes place due to non-zero masses of hadrons, right? Could you
Yes.
please elaborate on that? Because what I have read till now, the chiral symmetry breaking takes place due to the vacuum expectation value, because when you take this quark condensate, when you rotate them separately, they are not conserved. So could you please explain upon this
Yes.
mass dependence?
Yes, so there are two different things. So when you say it's broken by the masses, then this is usually called the explicit current symmetry breaking, right? So the Lagrangian is not invariant under this symmetry in the presence of the mass. Now, the vacuum expectation value spontaneously breaks the current symmetry, right? Meaning the ground state is not invariant, or more precisely, it spontaneously breaks the approximate current symmetry, right?
Yeah, okay.
So that's this bit. So in other words, the masses would tilt this potential, and then the vacuum expectation value would pick a direction in this slightly tilted potential.
Okay.
Does that make sense?
I didn't quite get it, but yeah.
So there are two different ways of breaking the symmetry. One is on the level of the Lagrangian. That's called explicit current symmetry breaking. That's done by the masses. And then there's one on the level of the ground state. That's done by the vacuum expectation value.
Okay, so you're mainly saying that there are two types of chiral symmetry breaking, and what I was talking is different from the one you said about.
Yes, maybe I didn't make this difference clear from the beginning, but in the most part of the talk, when I said chiral symmetry breaking, I meant spontaneous chiral symmetry breaking, right? Okay. I already accepted that there are small masses. Yes, it's explicitly broken, but very little. And then I'm only talking about the spontaneous chiral symmetry breaking, right? In the terms of a phase transition from a broken to a symmetric phase, right?
Okay. Yeah.
That's of course all for a given mass parameter in the Lagrangian. Let's keep this fixed, and then let's check where is the chiral condensate zero and non-zero.
Okay. Yeah, I get it now.
Okay.
So, meanwhile, there's a question in the chat box, if you can take a look at it.
But I only see my screen, and I have to go out of the full screen.
Okay, so Amit asks, could you explain shortly why solving QCD is a priority and what is the near future goal that we hope to achieve?
Well, when you say it's a priority, then it's, of course the question is compared to what. I would certainly think it's something important because we know it's a fundamental theory. It's part of the standard model, right? So when we solve QCD, we've learned something about nature on the fundamental level. That's probably reason enough to work on this. And what was the second part? The next goals, or was that the second part? The next goals?
What is the near future goal that we hope to achieve?
Yes, I mean, since I'm talking, I mean, there are many aspects of QCD, right? I mean, there's the whole vacuum QCD physics, which I haven't even talked about here. If we talk about applications to Neutron stars, then I could say it's become an even more active field now with the gravitational waves that we've detected. So some of the near goals are, for example, if you look at this, because we have this new window here, the mergers, one goal is to calculate properties like viscosity of these phases or equation of state, also for larger temperatures, right? To compare to the data from the mergers. That's one of the goals.
Now, if participants have any queries or doubts, you can share them. Any final questions?
I have one final question. So there are only few. According to me, there are only few results in QFT which are non-perturbatively exact. So will QCD be one of that? Is there something in QCD where the results would be completely exact, non-perturbative?
Well, lattice gauge theory does that, right? So that's, of course, when you say exact, lattice gauge theory has some limits that you have to do some continuum extrapolation. But if you forget about these things, that's a truly non-perturbative result, right?
But that's only in the massless region, right?
No, why?
Because you just said that lattice QCD is only applicable to the massless region. So.
No, the region without chemical potential.
Oh yeah. Okay. Yeah. Sorry.
Yeah.
Yeah.
Yes, of course. It's only valid there. I mean, there are other non-perturbative methods. I mean, in the introduction, you said that I'm also working on the so-called gauge gravity duality. That's another approach where one has some honest, strong coupling calculation, which sounds very promising. But the problem is, you can only do this for certain theories, and none of them is QCD. So you can do it in theories that are more or less different or similar to QCD. And of course, then there are some other, you can always include some non-perturbative effects with so-called Schwinger-Dyson equations. But to some extent, they make some truncations also. So it's usually in these difficult intermediate regimes here, it's not the full first principle result. Does that answer the question?
Yeah. Yes.
I think that's all then. Thank you so much, Professor Andreas, for giving us an amazing insight into quantum chromodynamics and neutron stars. We are grateful that you accepted our invitation today. I believe everyone present here would have learned a lot from today's discussion. Thank you, Dimple ma'am, for attending our talk and always supporting us. And to all the participants for showing your interest and sharing your time with us. If you want to know more about our other events, please visit our website, physicsclubsbnit.github.io. And it's time to say goodbye. Please stay safe. See you soon. Thank you, everyone. Bye.
Thank you, Bhavya. It was my pleasure. And thank you very much, sir.
Yeah, thank you very much also to everybody who attended and all the nice questions. Thank you very much.
Thank you.